to do is to ignore this problem. Essentially, that's the way it was done originally, and just pretend that the delta functions are allowed to have complex solutions. Actually, that turns out also to not be correct when you go beyond one loop. So what we really need to do is to reinterpret what we mean by the delta functions and what we mean by cutting. And the way we're going to do that is we're going to replace these delta functions by contour integration. It's really the more natural kind of object. The way you localize an integral in a complex space is not by imposing a delta function, but it's by doing a contour. Because when you do a contour integral, you're essentially picking out the value of the function at the pole. You're localizing it at the pole. So how does this work in one dimension, one complex dimension? We're going to have some contour integral. And it's going to be a little circle around some point, which I'll call V0. That means I have some circle of some small radius, delta. I won't be very precise about what I mean by delta here. So we notice that if we do a contour integral like that, and let's suppose we have some polynomial indices right here, in the numerator, and we have polynomial 2 in the denominator, where this equation has only a simple root at a, so the definition of C0 is this implicit equation, so that this object in fact has a simple pole. This denominator has a simple pole at C0, so we want this thing to go essentially going near values of A, near C0. So we know how to do this integral. We're simply going to get the numerator evaluated at C0, and we're going to get the Jacobian in the denominator. So remember that if we were doing a delta function, a real delta function, delta of f of x, then we're going to get, of course, the sum over the solutions of f of x equals 0, and we're going to get 1 over the absolute value of f prime of x, where that solution happens. So the very crucial difference here. That crucial difference is the absence of the absolute value size here. There's no absolute value here. You do a contour integral of an analytic function, you get an analytic function. And it's actually a crucial difference, and this is actually the correct way to think about it, and not this one. So you could imagine having some complicated definition of a delta function that extends into the complex plane and all that, but that's not what you want to do. You don't want those absolute values. So when I write down a delta function now, then what we're going to do is define what we mean by the delta function. So this is a new kind of complex delta function, no positive energy condition, and we're using the same symbol as we would for a real delta function, but what we mean by this is this contour integral around the solution of the same numerator and with a denominator that localizes the integral at the pole. So when we do this, we now have to do this not in one complex dimension, but in 4 complex dimensions. And the theory of multivariate complex integration has a lot of subtleties, but which would take us too far afield to even talk about. But if you imagine simply taking a 4-fold version of this, instead of having a circle, we now have a 4 torus that encircles the simultaneous solution. That's the contour of integration we want. And these simultaneous solutions are called global poles. One way of thinking about it is that you want to choose a parameterization for the loop momentum where you can factorize the denominators into a product of single poles in different complex dimensions, and then you can imagine simply doing the contour integrals independently in each of the dimensions. And of course, part of the process of doing that, the change of variables you need, will yield a Jacobian factor that's analogous to that derivative of polynomial 2 in the denominator. So if we want to think pictorially about what we're doing, we started out with a loop integral, where at least for the L0 component, it's easy to draw the contour of integration where the poles actually are. We're integrating along the real slice. Maybe I should use colored chalk here. integrating along a real slice, and the poles, which would otherwise be on a real slice, are slightly shifted away by the Feynman-Einstein prescription. And we're replacing that concept of integration in a certain sense in each of the components, although what we have to do, as I said, a change of variables first. We're replacing that by the integration around the global poles, which are sitting way off in the complex plane. They're nowhere near the real slice. So what we're replacing is, in case we have two solutions, we're going to replace it by a contour integral around those solutions. This is not a contour deformation. It does not leave the value of the integral unchanged. In fact, what it's going to do is take us from the integral, which has dialogues and branch cuts and stuff like that. It's going to take us and give us a rational function, which is very closely related to the coefficient. And the reason we're doing this somewhat obscure-looking operation, if I had simply started my lecture yesterday with this construction and said this is unitarity, then I think most of you would have wondered, what is this guy talking about? But I think you can see why this is essentially an operation of cutting and what the connection with unitarity is. So let's go back and do something useful with all this construction. Let's apply this cutting idea. So we have, if you can imagine, writing the amplitude in the abstract as the sum over Feynman diagrams and Feynman integrals. So we have these loop integrals on both sides of the equation. We start out with an object where we have an integral along the real slice, and on both sides of the equation, I want to make this replacement. I want to replace the contour along the real slice with a four torus encircling the global pole. So I want to apply quadruple cuts to both sides of that equation. So when we do the change of variables, when you do a parameterization of the loop momentum, of course there's going to be a Jacobian there. That's going to live in the numerator. When we actually localize on the global pole, there's going to be another Jacobian in the denominator in one loop. Those turn out to be essentially constants in that is just dependent on the external invariance, so we don't actually have to work them out in detail. On the left-hand side, we get a Jacobian, and that's going to be multiplied by a certain sum over the solutions of the equations, or equivalently the global poles in our new language. And then, as usual, when we cut a line, we have to sum over all the intermediate states that you go in, so we have to sum over felicities. But now, it's not enough just to sum over felicities because we don't know the identity of the particle that's circulating around the loop. So we also have to sum over the different kinds of species that can circulate in the loop. And we'll have a product when we isolate certain four selected propagators and we put them on shell. Well, what that does we're going to get a product of four amplitudes, because these lines are now on shell and they're on their physical states. I'll just label these A, B, C, and D. Now, in this particular picture, I've drawn them as all being massive, but they don't have to be. They could be, for example, we could have leg C being massless, and then what do we have here? We have our old friend, the 3-point amplitude. And everything is very nice because these momenta, remember our solutions are complex, so I've of course only shown you one of the loop momenta, but you can imagine when you shift that complex momentum by the external momenta which are real, then in fact all four of the cut loop momenta are going to be complex. So these two guys are complex, and everything is fine. We can find a non-vanishing value for our 3-point amplitude. So we can treat all the different boxes, whether the external legs are massive or massless, on the same footing. So we cut apart our loop amplitude into 4 free amplitudes, and we have to take the product of those things and sum over felicities and species, and that is going to give us the left-hand side of the equation. On the right-hand side of the equation, there's a specific integral that's been picked out. Exactly which one depends on which global poles we've chosen. Different boxes will have different global poles, and of course we're going to have to iterate over all of them in order to find all the coefficients. On the right-hand side, of course, we have the coefficient. It doesn't care about global poles or anything, it's just a rational function sitting in front. And we have, of course, the same Jacobian. And we have nothing in the numerator, so we're just going to have 1. It's going to be evaluating 1. That numerator polynomial 1 is just 1, so we're going to be summing it, and that's just going to